Wow, the year is flying by in Algebra 2, Trig, and we're embarking on one of our last chapters of the year. We're going to start a chapter on trig graphs, and today we're going to start with the sine curve. We're specifically going to focus on y equals sine of x, and then we're going to start to add coefficients in weird places and see what kind of effect it has on our graphs. But I've got a beautiful picture here for you to set the tone, and this is the most basic generic sine curve we could have. And what you're staring at right here in this red graph is what we consider one complete cycle. Okay, and what does one complete cycle consist of? Well, you'll notice we started with a root. Okay, that's important. The sine curve always starts at the origin, starts with a root, it then goes up and hits what I call a maximum point, and then it comes down and hits its second root. It goes down and hits its minimum, and then it finishes with the third root. So within one complete cycle, you're going to see a grand total of 3 roots, 1 maximum, and 1 minimum, and that's really important to keep an eye on. Now, the other thing I want to comment on this particular picture is you'll notice the x-axis is labeled in degrees right now. Okay, right now it's in degrees. We're not going to use degrees when we label these in class. We're going to always use radians, okay? So, and we have flashcards for this, and so I'm going to cross off 90, and I'm going to say that's really pi over 2 in radians. I'm going to cross off the 180, and I'm going to say that's really pi. 270, this is one of the more challenging ones. This is really 3 pi divided by 2, and then the last one, 360, is really 2 pi. So every time we do a trig graph, we're going to start off by putting these 4 famous hash marks on our x-axis. We've got pi over 2 and pi and 3 pi over 2 and 2 pi. And then once you get those hash marks labeled, we can go to town and start drawing, the rest of the curve. Now, I pulled up another picture here, a very nice one. This one, not only does it reiterate that the highest point the curve ever reaches is a height of 1 and that the lowest it ever goes is a height of -1, but it also shows you that the graph is what we call cyclic. It basically repeats the same pattern over and over and over again. This one starts all the way back at -2 pi. And what we've got here, from -2 pi all the way to 0, that right there is considered one cycle. And then from 0 all the way to 2 pi, that's considered two cycles. So this picture, you're staring at 2 cycles. And then the last one on this slide, I brought up a picture this is actually labeled in radians, okay? Believe it or not, this is in radians. It's just, when we talk about radians, we usually assume that it's in terms of pi. It doesn't always have to be in terms of pi. For instance, look at this root right here. Is the root at 3? No, it's a little bit bigger than 3. Guess what it is? It's about 3.14. So guess what? That's where pi is. And then this is, 6 plus a little extra. So that's where your 2 pi is. Guess where that min is? That's right at 3 pi over 2. So 3 pi over 2, it's between 4 and 5, but certainly closer to 5. And then last but not least, this max. What's that x-coordinate right there? Well, that's pi over 2. So that's about halfway between 1 and 2. So we're going to do a lot of work with radians. It doesn't always have to be in terms of pi, although it usually will be. Alright, so I've done quite a bit of work already here. I've drawn a lot of things, and maybe we need to hit the pause button just to kind of get caught up here and jot down not only the unit circle that we have here on the left side, but also just this very basic x and y axis that we have on the right side. And notice, like we said in the last slide, as soon as you draw that x-axis, we're going to go ahead and label the 4 critical points, pi over 2, pi, 3 pi over 2, and 2 pi. Those are our so-called big 4 celebrities and so forth. Now, as we get ready to talk about how do we create the sine curve, where did it come from, and all that jazz, really understand that it's the unit circle that drives all of this. That's the engine that drives the train. And the big thing we took away from the unit circle is it's the y coordinates on that unit circle that describe the values of the sine curve. Okay, in this case, sine of x. So as we go around the unit circle, we're basically going to ignore the x coordinates and let the y coordinates tell me everything I need to know. For instance, let's start right here at this first point. That's 0 degrees, okay? So when x equals 0 degrees, the y value is 0. Hence, we put a dot right at the origin. Now, as we work counterclockwise, we've got 90 degrees up here at the top. That's equivalent to pi over 2. And so the sine of pi over 2 is 1. That's why when x equals pi over 2, we put a dot up here at 1. That's its highest point. It never, ever goes higher than 1. Going counterclockwise, we land here. That's 180 degrees, also known as pi radians. The sine of 180 is 0. That's why we put a dot right on the x-axis. That's our second root. Let's see, down here, that's 270 degrees, also known as 3 pi over 2 radians. The y-coordinate is -1. Therefore, we're going to put a dot down here at -1. There's the height. That's our min. And then we continue to finish off the cycle. So 0 degrees is also synonymous with 360 degrees. Again, the y-coordinate's 0, so we'll finish with a dot. And then we're just going to connect it with a real nice, smooth, gentle curve. And this is one of the things we'll be very picky about in class tomorrow. Just make sure we're real nice and smooth and rounded. I don't want any straight TP-like lines. So that's where the sine curve came from. It's all came from the unit circle, and that's the engine that drives the train. Alright, now it's time to go grab that calculator. I don't care where it is, if it's in your book bag, if it's upstairs, if it's downstairs. Hit the pause button and go get it right now. We need to practice right along, hand in hand with what I do. The first slide that I want you to look at here is right here, this number 1 slide. So we're just going to go to y equals. We're going to type in sine x, close the parentheses, so hopefully your screen looks just like this. Step number 2, I want you to hit the zoom button. It's up at the very top row, middle button. And there's a whole bunch of things you've maybe used: zoom in, zoom out, zoom decimal. You've used hopefully some of these before, but our favorite one today is right here, choice number 7, zoom trig. So I want you to hit 7. And as soon as you hit the number key 7, hopefully the calculator will start graphing, and you'll see a picture like this. Okay, how many cycles do you see? Hopefully you just answered that question by saying 2 cycles. Okay, from here to here, that's 1 cycle. And then, let's see, from here to here, that's cycle number 2. So we saw 2 complete cycles. Now, something curious is happening. When you hit zoom trig, what really happened? Okay, what did the calculator do? What the calculator did is, it depended on what mode you were in. We've been in degree mode right along for the past several weeks. And if you were in degree mode and you hit zoom trig, the calculator automatically said that your x min was going to be negative 352.5. Now that's actually, the calculator's trying to say negative 360, and that's the left edge over here. And then the x max is approximately positive 360, and that represents the right edge over here on this side of your screen. And then the scale was 90. That just means every hash mark here represents 90 degrees, so on and so forth. However, if we were in radian mode, and we're going to start to do more and more radian mode, all you had to do, as soon as you hit zoom trig, the calculator automatically typed in an x min of negative 6.15. And you're thinking, what a random number. Could they have thought of a more random, obscure number? Well, actually, it's not that random at all. Negative 6.152285 represents what? Hopefully somebody out there just guessed it. It's negative 2 pi. Okay? And then positive 6.12 or 1522856 represents positive 2 pi. So the left edge is negative 2 pi, the right edge is positive 2 pi, and that's our standard interval that we like. Sometimes I'm going to have you go into x min, delete that number, and just put 0 in there sometimes, but not a big deal. How about this x scale? 1.57, again, random number, right? Actually, what that number is that's pi over 2, which is, again, equivalent to the scale we had over here in degrees. We're just counting by 90 or pi over 2 radians. Okay, now we're going to go over some important characteristics of the sine curve, and there's 3 mega properties that we need to hit today. And mega property number 1 is something we call amplitude, and that describes, its definition is the height of the curve above the midline. Alright, and you're wondering, what in God's green earth is midline? Okay, now typically the midline, especially today, is just going to be the x-axis. Later in the week or next week, we'll kind of tweak it a little bit. We'll start vertically shifting it up and down. But today, we're just going to describe, what's the maximum height of the curve above the x-axis. So, according to this first picture I have, let's see, what do we got here? So it's a little blurry, but I think you can read it. Okay, let's say right here's the x-axis, right? So the highest it ever goes above the x-axis right there is 1 unit. So on the standard sine curve, we're going to say that the amplitude is 1. All right, and it's just you find the maximum point, no matter where it is, you find the maximum point, and its height above the x-axis will tell you the amplitude of the curve. Now I've got a few other funky ones here. In fact, I pulled up one of my favorite pictures. This is a very overwhelming picture at first, but what you'll notice is I think there's 8 pictures here. You got the blue. You got the blue one, and then the pink one, the red one, the green, the bluish teal one, yellow, gray, and black. So there's 8 curves, and all of them they're all sine curves. How do you know they're sine curves? Well, guess where they start? They start at the origin, okay? And then they all have different amplitudes. The blue one has an amplitude of 1. The pink one has an amplitude of 2, because if you're following the hash marks here, it's a height of 2. The red one has an amplitude of 3. The green one's got an amplitude of 4, and so on and so forth. The tallest one up here, the black graph, has an amplitude of 8. So it's just a matter of finding the maximum point and asking yourself, how high above the x-axis is it? All right, mega property number 2 is what we call the frequency of a sine curve. And basically, this is the number of cycles completed at 2 pi. And that's assuming that we started counting the cycles when x equaled 0, okay? So it's the number of cycles completed at 2 pi. Again, hit the pause button. Make sure we get these definitions completely written down in our notebook. All right, no shortcuts here. The first picture I pulled up gives you a really nice glimpse of a curve that has a frequency of 1. Alright, so what you'll see here, pretty self-explanatory I think. The curve starts at 0, and what we're going to do is there's your max, your second root, and then down here we hit the min, and then we hit the third root, and as soon as you hit that third root, you know you've completed 1 cycle. Alright, so by the time I got to 2 pi, I've only got 1 cycle, so I would say that my frequency equals 1 for this particular graph. Of course, that's going to change later today. Alright, here's my next graph. We blew it up as big as we could. Now, let's count the cycles. We start at 0, okay, and by the time you got to 2 pi, okay, and we're going to ignore everything that comes after 2 pi. We're going to pretend that part's not there. How many cycles do you see? Alright, well, let's see, right there, that's 1 cycle, okay, and then from here to here, that's another cycle. So I would say that the frequency is 2 for that particular picture. Alright, let's make sure we get that picture in our notebook. We'll sketch it the best you can, and then just write down that the frequency was 2. Again, I didn't label the x-axis in terms of pi, but this root right here was just a little beyond 3. So that's your pi, and this is 2 pi over here. Alright, moving right along. New picture here. And I tried to compare and contrast the original sine curve. So let me trace it in red. In red, here's the original sine curve. Alright, that's the basic one. And then in blue, I've got this giant monster that gets really tall. So there's a few special characteristics. First of all, on that blue graph, how many cycles do you see? Do you even see 1 cycle? No. Actually, what you see is you see half of a cycle. So I'd say the frequency is 1/2. And just as a side note, to make sure we didn't forget what we just talked about 2 minutes ago, what's the amplitude of this picture? How tall is it? That highest point, distance from the highest point to the x-axis, that's 3 units. So the amplitude is also 3. I think I've got one more picture here. Yep. All right. A little blurry here. Don't worry about copying this one down, but I wanted to compare and contrast. And what I want to assume here, let's assume that that's 2 pi right there. So then that would mean this right here is pi. All right. So ignore what's on their x-axis and just go with pi and 2 pi. So the green graph, I'll use G for green here. That represents the standard sine curve, has a frequency of 1. Let's see, the blue curve has a frequency of 2. And how about that red curve? How many frequencies do you see there? Let's see, that's the completion of the first, completion of the second, completion of the third, and then one more, we got 4. So I would say the blue curve has a frequency of 4 cycles there. Our third mega property is something we call the period of a sine curve, and it's the number of radians it takes. Whoops, let's see. Can I spell radians? That's the question. Number of radians it takes to complete just 1 cycle. All right, so we're going to keep track at what moment, assuming again that we started at 0, at what moment did I complete that first cycle? Okay, so let's take a look here. The first one we got written down here. We started right here. There's the second and there's the third root. As soon as you hit that third root, you know you're done. So I would say this one that the period is 2 pi. It took me exactly 2 pi radians to complete that first cycle. Take a look at another one here. All right, when did you complete the first cycle? It looks like right there. Let's see, right here I should say. That's pi, okay? That's where the third root is. first root, second root, third root. That's where we got the pi. So I would say there the period of that graph is pi radians. That's how many it took to complete one cycle. Let's see, do we have more examples here? Oh yes, okay. Here's a good example, and they're going to do this a lot. They're going to give you more picture than you really need. So if they give you anything, I want you to instantly scribble that out if they ever give you more picture than you need. Let's start with the pink graph. The pink graph finishes its first cycle right here. That's a little beyond 6, so we know that that's 2 pi. So for the pink graph, we know that the period equals 2 pi. Now how about the green graph? Okay, well let's see. Let's see if we can trace that green one. It's going to start here, here, and it's going to finish right there. Ah, boy, let's see. I don't know how many radians that is. That's a tricky one, isn't it? Well, let's see. How many cycles do we have? What's the frequency? There's my second cycle right there. There's my third cycle right there. So we completed 3 cycles within 2 pi. What I'm going to do is I'm going to take that 2 pi, I'm going to divide it by how many cycles I got. And that is going to tell me the period of my graph. So that radian right there, guess what that is? That's 2 pi over 3 radians, or approximately 120 degrees. So if all else fails, and it's hard to tell by the picture, just count up the number of frequencies you got and do 2 pi divided by your frequency. So let's kind of turn that into a little formula here at the end of this slide. Don't let me forget. Looks like I've got one more picture here, at least. How many cycles do we see? Let's see here. There's number 1. There's number 2. There's number 3, and it looks like we've got a grand total of 4, and that's again a little past 6, so that's where your 2 pi is. So let's do 2 pi divided by the number of frequencies. I'm going to simplify that fraction and get pi over 2. So that means right here, this radian right there is pi over 2. That's how many radians it took to complete the first cycle. Period is pi over 2. Looks like I just a little wacky here. I just pulled up one more picture from online. Just to show you what's coming in a few years if you stick with math. These sine curves, when you start getting into 3-dimensional fields, turn into real wavy creatures like this one. This is kind of an exciting 3D graph that I just wanted to throw at you. But before we go too far, let's generalize this formula. The period of a trig graph, or I should say a sine curve, is going to be 2 pi divided by the curve's frequency. Let's put a box around that. Let's really highlight that in our notebook, and that's going to be something that'll show up on our bite-sized quizzes. Okay, before we do some sketching here, I just want to recap from the basic sine curve. This is the original y equals sine of x curve. And what are all the properties? Well, the basic curve has an amplitude of 1. He has a frequency of 1, because that's the number of cycles you see by the time you hit 2 pi, and it's got a period of 2 pi radians. That's how long it takes to complete the first cycle. The domain is actually all x values such that x is an element of the set of real numbers. And basically what that means is the graph goes on forever and ever and ever. It just continues to repeat the same cycle over and over again. However, the range is very different. All y values such that -1's less than or equal to y, which is less than or equal to 1. And basically what we're saying, we use -1 because that's the lowest it ever goes, and then we use +1 because that's the highest it ever goes. If we continue to graph this rascal, it would just continue to do this over and over and over again until it hit infinity. Now, as far as some of the sketching goes, it's really important to remember that this graph starts with a root, goes to a max, second root, min, third root, and that's the pattern I'm going to continue to verbally repeat as we're sketching these. Now that we've mastered those 3 mega properties, how are they going to show up in the equation? Well, our standard form of a sine curve is going to be coefficient A times the sine of quantity B times x. And I want you to make sure that the way that I just read that, it's coefficient A times the sine of quantity bx. A represents the amplitude. In fact, let's do this. The absolute value of A represents the amplitude of the curve. B represents the frequency of the curve. And then you won't be able to see the period in the equation, but all you got to do is 2 pi divided by B, because that's your frequency, will tell you the period of the graph. And if you're on a quiz, you could either say 2 pi divided by B or 2 pi divided by F. You're going to get full credit either way. So let's go ahead and let's try to sketch our first one. We're going to start off real simple. Let's do y equals 2 times the sine of x. So the first thing I'm going to say to myself is that the amplitude is 2. That describes the height. The frequency is 1 because of this coefficient right here. And then the period is going to be 2 pi divided by that frequency. So 2 pi divided by 1 is just 2 pi. Now, as I get ready to graph this, we're always getting in the habit. We're going to label those 4 main points. We've got our pi over 2. We've got our pi. You're going to be doing this in your sleep. You're going to be doing it so many times. So the only thing that needs to change, instead of a height of 1, I've got to go up to a height of 2 and as low as negative 2. Now what I do after that is I'm going to just talk myself through it. Okay, I'm going to start with a root, go up to a max, root, min, root. And once I get those 5 points done, then I'm just going to be real careful and smooth and sketch that curve like such. And I got one complete cycle. For my second example, again, we're going to keep it really simple. Let's do y equals sine of 2x. And I should have stated on the last one that desired interval 0 to 2 pi. That's kind of like the domain they want you to limit yourself to. So whenever they do a sketch, they'll tell you where to start and when to stop it. So the first thing I'm going to say to myself here is now I've got an amplitude of 1 because of that coefficient. I've got a frequency of 2 because of this rascal. And then the period is going to be 2 pi divided by 2, which in this case turns out to be pi. So I think this one's a little bit trickier in my estimation. So we've got our pi over 2, we've got our pi. If I'm going too fast, just hit the pause button, give yourself a chance to catch up. Finish with 2 pi. Now, so here's what I'm going to say to myself. All right, I need to finish that first cycle by the time I get to pi. So I'm going to start with my first root and end with my third root. Halfway between those 2 roots is my second root. Halfway between my first 2 roots is a maximum, which in this case is a height of 1. And then halfway between my second and my third root is my lowest point, my minimum. Okay, so I'm just going to go ahead, I'm going to sketch that nice curve there, and then I'm just going to talk myself through it again. I'm going to repeat that same pattern. I'm going to say, okay, let's start with a root and end with a root. Halfway between my first and third roots is a second root. Halfway between my first and second roots a max. Halfway between my second and third roots is a min, and then I'm just going to connect that real nice smooth curve, and we've got a frequency of 2. Our third example is a little trickier, and there's 3 key components that we want to go over. First things first. Now remember, the amplitude is the absolute value of that leading coefficient. So the amplitude's actually 3 if they ask that on a multiple choice question. My frequency is this coefficient right here. So I'm just going to say 1/2. And then the period's real interesting. It's 2 pi divided by 1/2. And 2 divided by 1/2, actually it gives you 4. So 4 pi. It would take 4 pi radians to see an entire cycle. And we're going to assume that they just want to see 0 to 2 pi. So if I show them more than 2 pi, then I'm going to be in trouble. So in fact, by the time we get done graphing, we're only going to see half of this curve because of that frequency being 1/2. Anyway, let's label up that x-axis, pi over 2, there's pi, there's 3 pi over 2, and we'll finish with 2 pi. Again, we're just going to talk ourselves through it. The question is, what does this negative rascal do? What impact does that have on the graph? What happens is, and you're always welcome to plug it in your calculator and hit zoom trig to kind of get a feel for it, but what it does is that negative, okay, and we'll make a little note here, reflects the graph over the x-axis. So what's going to happen is, instead of seeing that max between the first 2 roots, I'm going to see a min. And so here's how I'm going to talk myself through it. I'm only going to see half the picture, and it's going to get reflected over the x-axis. So picture your normal sine curve that looks like this. We're only going to see half of it. So essentially, we're scribbling out this much, and we need to reflect it over the x-axis. So here's my first root, here's my second root. Halfway between those 2 roots is my minimum of -3. So I'm going to scale the y-axis. There's -1, there's -2, and down here's -3. And that's all it is. Again, you're more than welcome to plug that function into your calculator and graph it, zoom trig, see what it looks like. But we see half the cycle. The amplitude is 3, the distance from here to there. And the negative reflected it over the x-axis. So that's the final product.